Hello, my name is Christian Conrad and I'm an assistant professor at the University of Bristol. I'm presenting today a joint work with Lydia Binti Khalil, who worked with me on this problem in the context of her BSc thesis. So this work is about constructing large matchings via query access to a maximal matching oracle. So ultimately this work is about matchings, and before I go into the details, I would first like to recap a little bit the definitions that we need for matchings. So let G be a graph, then a matching is a subset of non-adjacent edges. So for example, the picture on the right, we see that the two red edges don't form a matching because there's a vertex that is included in two matching edges. That's not possible. A matching is maximal if we cannot enlarge the matching by simply adding an edge outside of the matching to it. So for example, on the picture on the right, we see that this is not a maximal matching because we could include the edge that connects the rightmost two vertices into the matching. Now, a matching is maximum if it is of maximal size, that is, it is at least as large as any other matching in the graph. Now, there's an important relationship between maximal matchings and maximum matchings. We know that the size of a maximal matching is at least half the size of a maximum matching. Now that's an important inequality, and we will use this a little bit later. In fact, already on the next slide. So our goal in general in this work is to compute approximations to maximum matching. We want to find matchings that are as large as possible. In particular, we want to find matchings that are better than 1/2 approximations. So matchings that go beyond maximal matchings as an approximation for maximum matching. Now, one motivation for this work is the following observation. So we know that in many computational models, in particular data streaming, and I will come back to that a bit later, but also many distributed models, we see that computing maximal matchings is rather easy, and computing larger matchings, approximations to maximum matching that are, say, 1 minus epsilon approximations or beta approximations, is more difficult. So, for example, in the data streaming edge arrival model, so a data streaming algorithm is characterized by the fact that input is accessed only in a linear fashion, so item by item. Now, in a graph stream typically looks as follows. So we have some input graph, and the algorithm simply sees a sequence of the edges of the graph in arbitrary order. Now, the objective in the data streaming model typically is that we want algorithms that process the input in few passes, hopefully 1 pass, maybe 2 passes, 3 passes, a constant number of passes. And in particular, the algorithms are only allowed to use small space. Now, small space, definitely little o of the length of the input, but potentially even less. So here's a streaming algorithm for maximal matching. We can simply insert the current edge. So while processing the stream, we insert the current edge into a matching if that's possible. So if the two endpoints are not yet matched. So this essentially constitutes the greedy matching algorithm. In other words, the greedy matching algorithm can be implemented in the data streaming model, and it produces a maximal matching. It uses space order of n roughly, order tilde of n. Now, in the data streaming world, we have the current state-of-the-art results. So first, if we look at bipartite graphs, we see that in a single pass, in fact, the best algorithm we know that uses only sublinear space produces a 1/2 approximation, and that is the greedy algorithm. And it's a major open problem in this area to improve on this approximation factor of 1/2. Then we see that in 2 passes and 3 passes, there are ways to improve on the approximation factor of 1/2. We also see that we can compute a 1 minus epsilon approximation if we allow order of 1/epsilon square passes. Now, for general graphs, there are also results. They are slightly weaker. For example, in 2 passes, we have a worse approximation guarantee than for bipartite graphs. And in particular, for 1 minus epsilon approximations, we have a runtime that is exponential in 1/epsilon. Sorry, I meant the number of passes are exponential in 1/epsilon. Now, the key observation here is the following. Most of these algorithms, and in fact including previous works, not only the ones that are displayed in this table, they essentially do the following. they run the greedy algorithm, the greedy matching algorithm, in carefully selected subgraphs in each pass, and thereby collecting edges. Now, the output then is produced by simply selecting the largest matching that can be found among the edges that are stored, that are returned by the invocations of greedy. And this leads us to the research question that we ask. We would like to know how large a matching can we compute if we solely invoke greedy in each pass. Now, we studied this perspective as follows. So we model the whole process of querying or of computing maximal matchings via a game between a player and an oracle. We have the following matching game that we study in this paper. So a player is allowed to submit a query to the oracle. So this whole game is rounds based. We have overall R rounds. So in each round, a query is submitted to the oracle. And the query consists of a subset of the vertices of the input graph. Now the oracle needs to respond with a maximal matching in the subgraph, in the induced subgraph by this vertex set. So again, initially, the input graph is not known to the player. The player only learns about the input graph by the answers from the oracle, that is, by the edges returned from the oracle. Now, in the end, the player has accumulated a certain number of edges and would return the largest matching that can be computed among the edges that the player has learned about the input graph. And we measure the performance using an approximation factor. Now, the question we'd like to ask is the following. What is the trade-off between the number of rounds that we allow in this matching game and the approximation ratio that can be achieved? Now, before we go into our results mainly consist of lower bounds. Let's first look at some upper bounds for our matching game. Now, for algorithms here, we see the following. In a single round, we can, of course, query the entire input, vertex set. Then this yields a maximal matching in the entire input graph, and we therefore immediately get a 1/2 approximation. So 1/2 approximation in one round is easy to obtain. Now, there's no particular algorithm known in the literature that would use two invocations of greedy that could be implemented in this model, but so we know that the 2-round situation, we have at least a 1/2 approximation. In 3 rounds, there is a data streaming algorithm analyzed by Kale and Tirotka, and this data streaming algorithm can be implemented directly in our query model, and this yields a 3/5 approximation. So 3 rounds, we get a 3/5 approximation. Now, it's also possible to obtain a 1 minus epsilon approximation, and this can, for example, be done by implementing a known streaming algorithm that originally runs in 1/epsilon to the 5 passes. This can be adapted to our model to run in 1/epsilon to the 6 passes. So we can even get a 1 minus epsilon approximation in our model. Regarding general graphs, there are no particular upper bounds known to us potentially, except a 1-round 1/2 approximation, which is again simply implementing the greedy algorithm, querying basically the whole input graph, all vertices. Now let's put our lower bounds in perspective to these upper bounds. So we give the following lower bound results. Regarding the 1-round 1/2 approximation situation, we show that this is optimal, and this is also not very surprising. Now, we know for 2 rounds the approximation factor is at least 1/2 that is possible, that could be achieved, and we show that in fact 1/2 is best possible. That is, a second round doesn't help us to improve on 1/2. For 3 rounds, a 3/5 approximation is known, and we prove that this is in fact optimal. 3/5 is the right answer for 3 rounds, and this is our main result and the most technical result of this paper. We have for a 1 minus epsilon approximation, we know that it can be done in 1/epsilon to the 6 rounds, and we prove that omega of 1/epsilon rounds are needed for such an approximation. Now, this all holds for bipartite graphs. For general graphs, we show that our model is not very well suited for general graphs, in fact. We show that if you would like to compute an approximation ratio strictly better than 1/2, then you need omega of n rounds to achieve this in our query model. Okay, so this brings us to the outline of this talk. I will go through our three results. First, I show that omega of 1 over epsilon rounds are needed for 1 minus epsilon approximation. Then omega of n rounds are needed for 1/2 plus epsilon approximation in general graphs. And finally, our main technical result, it's a 0.6 approximation lower bound for 3 rounds in bipartite graphs. Okay, so the lower bound for computing a 1 minus epsilon approximation. We proved the following theorem. Any query algorithm with approximation factor 1 minus epsilon requires at least 1 over epsilon minus 1 queries, even in bipartite graphs. And the graphs we look at or we use for constructing this lower bound are semi-complete graphs. So consider such a semi-complete graph on two C vertices on the left and C on the right. So semi-complete graph can nicely be drawn in such a fashion so that a vertex on the left side is connected to all vertices on the right side that are on the same level or below, like located on the same level or below. So for example, the topmost vertex on the left side is connected to all vertices on the right side, and the bottommost vertex on the left side is therefore only connected to one vertex on the right side. Now, a semi-complete graph has a unique perfect matching, and this is of size C here. And in particular, if we don't have an optimal matching, a perfect matching, so suboptimal matching, therefore constitutes at best a C minus 1 over C approximation. So it consists of at most C minus 1 edges, therefore we have a C minus 1 over C approximation at best. So what this means is we really need to get the edges of the perfect matching, otherwise we would only produce a C minus 1 over C approximation. But this is difficult. So the insight here is that any query gives at most one edge from M star, one perfect matching edge. And here's an example. Suppose we query the red vertices, then the oracle needs to return a maximal matching in this induced subgraph. And we can basically match the vertices as follows. So we always match sort of the top vertex on the left to the bottommost vertex on the right, and we continue sort of in this fashion, and we go downwards on the left side and upwards on the right side. And in doing so, it's not hard to see that we output at most one sort of horizontal edge, so one edge of the perfect matching. But that means if we want to compute a C minus 1 or better than a C minus 1 over C approximation, then we need to have at least C rounds, of course, because we can only produce one optimal edge in each round. This can be rephrased, for example, setting epsilon to be 1 over C plus 1, we see that 1 over epsilon minus 1 queries are needed. And that's basically already it. Now we can, of course, take multiple disjoint copies of this gadget if we want to have a hard instance for arbitrary n. Okay, so this is quite a simple lower bound. And in fact, the lower bound for general graphs that we need at omega of n queries to improve on 1/2 is similarly simple. So the result that we prove is as follows. So any R-round query algorithm for general graphs has an approximation factor of at most 1/2 plus R over n. Now, the graph that we use to see this result is a bomb graph on n vertices. So such a graph consists of a clique on n-half vertices, so the inside constitutes a clique, and then these n-half vertices are connected to the outside vertices. There are also n-half of them, and they're connected via perfect matching. Now, the outside edges form a perfect matching, so these are the good edges that we would ideally like to have. The inside edges, they are really not very good because each inside edge blocks two optimal outside edges. So for every inside edge we take into the matching, we cannot take two of the good outside edges here. Now, it's not hard to see that if we had a matching of size 1/2 plus, or if we have a 1/2 plus R over n approximation, then this we necessarily managed to obtain R outside edges. But then the insight is the following. Every single query might return at most one outside edge. And this can be seen as follows. So for example, here we have a query consisting of the red edges. then the answer from the oracle could be as follows. The oracle first matches up or pairs up the vertices inside the clique, so like this. And this means that if we query an even number of vertices, then we would only return edges from inside the clique and no edges outside. But here we have an odd number of vertices, so we have 5 vertices from the clique, so we can't pair up all of them. So at most 1 outside edge per query would therefore be returned. And that means we need R queries to get a 1/2 plus R over N approximation. And that's already it. Okay, now a few remarks here. So these lower bounds, both of them are very simple, and in fact these lower bounds even hold if the input graph is known by the player. And for this reason they also hold for randomized query algorithms. So in that sense they're simple but very strong. They hold also for randomized query algorithms. Now the lower bound that I'm going to present in a minute about the 3 rounds lower bound for bipartite graphs, the 3/5 approximation lower bound. So the argument is much more subtle. In particular, the oracle builds the graph as we go along, and the graph depends on the queries submitted by the player. This means that this lower bound really only holds for deterministic algorithms, this 3-round result. Okay, so regarding this lower bound, I would first like to talk about an upper bound that actually shows that we get a 3/5 approximation in 3 rounds, and that works as follows. So suppose the first query consists of simply all the vertices in the input graph, and this produces a matching M. So suppose this is our matching M here, connecting the A and B vertices. Then we look at this sort of, in bipartite graphs we have a nice structure here, and the structure is that we can look at a subgraph here on the left side, so the matched A vertices and the unmatched B vertices. And what we do is we run, query now in this specific subgraph, which would return additional edges. Now, what we are doing here is essentially we're going to find augmenting paths, 3 augmenting paths. Now we mark specific B vertices that are matched in our initial matching M. We mark those B vertices that are endpoints of paths of length 2 in this matching M and ML together. And now our aim is, our third query, we attempt to match these red B vertices, so find a third edge to complete a 3 augmenting path. So we run a query on the right side in this induced subgraph. That's between B prime and the unmatched A vertices in the matching M. And we might find this specific edge. So using 3 queries, or 3 times 3 maximal matchings here, we actually found here 1 3 augmenting path. We can augment this specific edge in the middle and increase the size of our matching from 4 to 5. And it can be seen that this indeed, if we do a formal analysis, produces a 3/5 approximation. Now, here's a hard instance for this algorithm that shows that the algorithm is indeed not better than a 3/5 approximation. So this algorithm, this hard instance looks as follows. So first we see that the matching M produces already in the middle here, matching constitutes a matching of size 3. We see that the best matching we could produce in this graph is of size 5. That is, initially, from the beginning on, we already have a 3/5 approximation. Now what this example shows is that what the algorithm does is the additional edges that it produces won't allow the algorithm to increase the size of the matching. We see that if we query the first matching on the left side, we get this specific edge here, that's diagonal edge. And then we see we have only 1 path of length 2, so we highlight the red vertex, so only a single vertex, and this is the endpoint of a path of length 2. But then we see that in the subgraph on the right side, this highlighted vertex doesn't have even any edges. So the matching on the right side we might obtain, this MR, would be the empty set. So we can't improve the matching of size 3. So this is a worst case example for the algorithm, and we will see that our lower bound construction uses a similar method as this worst case example here. So our lower bound construction, the idea is the following. we will bound the knowledge about the input graph that the player could obtain after each query. So this is captured by a structure that we call a structure graph. And we always ensure that the knowledge about the input graph is so that we could potentially include or add a perfect matching to this specific structure to make sure that the input graph has a large matching that the player isn't aware of. So for example, after the first query, we make sure that, so the picture down here on the left, all that the player knows is that there exists, there is a matching of size 3 in this input graph, and we don't commit to any other edges, or the oracle doesn't commit to other non-edges. So all that we return is a subset. What the player will learn is a subset of the edges M here that we see here. Now on the picture on the right, we see that we can extend this knowledge that the player might have gained by a perfect matching. So we can include these 5 edges. The player knows at most 3, a matching of size 3, so that would constitute a 3/5 approximation. Now, of course, the structure that we represent here, that's up to isomorphisms. So the player, of course, might not exactly query a certain set of vertices that leads to this structure, but up to relabeling the vertices, it is indeed only this structure that the player can learn at most. After the second query, we are in this interesting situation, so we can, again, up to isomorphisms, we can show that all the player knows are the edges, the 3 black edges from the first round and the additional red edges. And the player also knows that the other edges between B4, A3 and B4, A2, they definitely don't exist in this structure. So this, the absence of edges is learned because matchings that are returned are maximal matchings, and this allows us to determine that some edges are definitely not in the graph. Again, we see on the right side that we can include these 4 blue edges and form a large matching of size 5 in the input graph together with this edge A2, B3. So we're still not better than a 3/5 approximation. Now in the third query, it's a little bit more tricky because we can't just have one structure graph that captures the knowledge of the player in all cases. So we need a few case distinctions, and we need to sort of make sure that we group the cases in a clever way together because there are just so many cases. So here's an example. If the query includes B1, B2, B3, then we see, for example, that we can make sure that the player only knows the structure on the left with the 2 orange edges included. And again, if we add the blue edges, we would have a matching of size 5. Without the blue edges, we would still only have a matching of size 3. So there are plenty of cases to go through in this case. Now, the key technique here is that the matching game that we study has some very interesting structural properties. So we can eliminate many cases with many observations about this game, and this is one of the key contributions of this paper. Okay, good. Now here are a few open problems. One open problem is the question as to whether we can compute in this matching game a maximum matching, not an approximation, in little O of n square rounds. Now we can of course do that in n square rounds because we could use in each query we could learn one different edge in the input graph. So O of n square is easy to compute a maximal matching. The question is whether little O of n square is sufficient too. Can we prove that omega of 1 over epsilon square rounds are required for computing a 1 minus epsilon approximation? So far we only have a lower bound of 1 over epsilon here. Now as an outlook, so we are interested in extensions. So we're looking only at vertex queries. So how about edge queries instead of vertex queries? So this would allow for slightly more applications. There are more algorithms that would fit into this model. And of course randomization. So the 3-round lower bound is rather complicated, but only holds for deterministic algorithms. A randomized argument would be really great here. And thanks for your attention.